All right, we are recording. You can go on ahead, Adriana.
Okay, thank you so much. So hello everyone, I'm very happy to be here. I'm a big fan of goals. So I'm happy that you are all part of this new community. So my name is Adriana and I just finished my PhD and I'm going back to Europe in Leuven. So if you ever are over there or want to give a talk, just contact me and I'll try to make it happen. But today I will talk to you. I guess this is the second lecture that you have on Neumann algebras, but this will be on the Bicommutant theorem, which is a very important theorem, which is this theorem that started it all, almost. Okay, thanks. Yeah, so yesterday you were introduced to more of the analytic side of Neumann algebra. Today I'll show you a little bit more the algebraic side. So I'll start with some definitions, which if you've never seen this, you may not know how it relates, but it all will come together in this theorem. Okay, so let H be a Hilbert space. So you have seen this probably in algebra, so that if you take two elements in your H, you can consider its commutator. So the commutator of x and y is simply xy minus yx. You say that x and y commute if this commutator is 0, so that xy is yx. All right, so so you have these four elements, but we're now going to consider it for subspaces. So you can do it for a general set, but we're considering subspaces. So for a subspace, let's say X in H, so a collection of sets, the commutant of X in V of H, which will be denoted by X prime, is okay, it's going to be defined as all the elements in V of H that commute with every element in X. So such that the commutator between Y and X is 0 for every X in X. So this means that, or this would imply that xy is yx. So you're looking at every element in V of H, so in a bigger space than X, that commutes with elements in X. So if X was a billion, in particular, X would be contained in this commutant, but that's not always true. Okay. So this is the commutant, which is very related to the commutator, which you've probably seen in algebra. But today, we will consider the commutant, but moreover, the double commutant. So the double commutant of X is simply the denoted by double prime will be the commutant of the commutant. So I don't know if you see up there. Okay, maybe you see this clearly, but put it here. So you take all the elements that commute with X, and then you consider the elements that commute with those elements. So double commutant. So that's why we call it double prime. Okay, so let's see some properties of both the commutant and the double commutant. The first one is that X prime is always, so the commutant is always a unital subalgebra of V of H. So regardless of the structure of X, it's always an algebra. So if you take, let's say, y1 and y2 in X prime and X in X, you always have that y1, y2 is still back in the commutant. So you just have to check that it commutes with every single element x in x. And then you can see that, well, y2 commutes with x, and y1 commutes with x, y1, y2. So it has at least this structure. It's always unital because the unit is in B of H and it commutes with every single element in X or part in B of H. So it's always contains the identity. And this is without any other property of X. So this is independent of X. It is a star subalgebra. So X prime is a star subalgebra.
Hey, Ariana,
Yes.
on these later boards, could we maybe write a little bit bigger?
Yes, thank you.
Thank you.
So should I rewrite this or is this okay? I'll just rewrite it. Okay.
Yeah, maybe a little bigger. Yeah.
Okay. So if you have to check the algebra structure, you can take two elements in X and X in X, and then you just have to check that the product lands back in X prime, so that it commutes with every element in X. So we take y1, y2 times X. Well, y2 commutes with X, and y1 commutes with X. So you have that the product also commutes in X. And then the identity again is in X prime because the identity in B of H will commute with every single element in B of H, so in particular X as well. Okay. Is this better? Okay. So so another one is that this may not be a star subalgebra, but if X is closed under the star, so we say X is closed under taking adjoints. Then X prime is a star subalgebra, a unital of B of H. And that's because, well, if let's say y2 commutes with X and X star is in okay, so let me just do this one here. So if you have y1 in X prime, or y, say, and X. Next, you want to check that y star commutes with X. But this is true if and only if after taking the star, we have X star y equals y X star. But because X star is also in X, since X is closed under star, and y commutes with everything in X, you have that this is true, and therefore this is true. Okay. And then the other one is the following. So X is always contained in the double commutant. You can check this. So you take an element in X and an element Y in the double commutant. And Y in the commutant. You just have to check that these two commute. So let me do this. So if X is in X, you want to check that X is in the double commutant. So remember that this is the commutant of the commutant. So you need to check that it commutes with X prime. But by definition of X prime, X and Y commute. So X is in the double commutant. And moreover, it's actually contained in the double commutant of double commutant, and so on. Turns out that the opposite inclusion is also true. You can check that. And then you also have this other rule. So X prime is contained in the third one is equal to the rest when you start doubling. So this is why we only consider X, its commutant, and its double commutant. The others are equal to each other. And you can, this is just, you can check this algebraic. Just not algebraically is fine. And then the last one, the right, is that if x is a subset of y, then the commutant of y prime is contained in the commutant of x prime. Oh, of x, sorry. So if you take an element y here, in the commutant of y, that means it commutes with everything in y. So then, in particular, it commutes with everything in x. So it's back in here. So this is the commutant, some properties mostly of the commutant, but also of the double commutant. And this doesn't seem now, but these have some analytic implications that we'll see a little bit later today. But we'll go through some examples of computing commutants and double commutants today before we get into the theorem. I didn't say it, but if you have a question, please feel free to interrupt. Let me know if you do have questions now before I erase the first board. Okay, so the first one, let's look at B of H. So, what we see there. So for those following the notice model, this is example 1.2.2. Okay, so first, sorry. So let H be a clear space. And we're going to denote by 1 the unit in B of H. So the map that sends side to side, let's say. Okay, so this one's not hard to see, but if you take the multiples of these identities, so just multiples of 1, so if you take the element psi, alpha times 1, it will send it to alpha psi. The commutant of this is B of H. Every single operator, every single element of B of H will commute with just 1, and therefore with any multiple of 1. So this one's not hard to see. And then the opposite implication is also true. By that I mean that the commutant of B of H is also multiples of the identity. So we'll define it later, but in this case it means that B of H is a factor. So everything, if you're an operator and you commute with every single other operator in B of H, you have to be a multiple of the identity. So this can be done in general, and you have an exercise that does it in more generality that I'll show you today, but I will do the finite dimensional case here. So here we're going to assume that H is just Cn. And so in this case, B of H is nothing but matrices. So maybe you've seen this proof in the matrix case that says that, well, if you are a matrix that commutes with every other matrix, you're just simply a multiple of the identity. Okay, so I'm going to set some notation before I show you this. So let Eij be the matrix such that the entry Ij is 1, and everywhere else is 0. You have a 0. So you have the following two properties of these matrices, which I'll let you check on your own. But if you multiply two of these, let's say Eij and Ekl, you get Eil only when j equals k, and otherwise you'll get 0. And the other one is that if you multiply Eii times any matrix A, and you multiply then by Ejj, you obtain on the ith j entry, you'll obtain the ith j entry of A, and everywhere else you'll obtain a 0. Okay, so this is for any matrix A. So let me do this. So this one I'll let you check, but I'll show you now the proof that the commutant of B of H is simply just C. So let A be a matrix with the commutant of these matrices. So what we want to show is that A has to be a multiple of the identity. So what we'll show first is that on the off diagonal, so anything that is not the diagonal, we have a 0. So if you look at the ij entry, okay, so the first thing is that the ij entry of A, you have multiplied by the eij matrix is equal to this quantity here, so this matrix here, ei and ejj. But now you know that A commutes with any matrix, so in particular it commutes with these matrices. So you have ei, ejj, A. But now you know how to multiply these two matrices. So what you obtain is that you will get eij times A only if these two coincide. So what it means is that if I is distinct from J, this will be a 0, and so the ith J entry of A will be 0. So the only thing right now what you have is that the only thing that is non-zero happens in the diagonal. So your matrix A is diagonal. But you want to show it's a multiple of the identity, so that means that you need every single entry in the diagonal to be equal. So let's see, let's show that. So if you look at EII times EII, okay. All right, so using the second equation, you see that this is EII and EII, something like that. Okay. All right, and so what you can do is insert here make this matrix into two matrices. So let's say EIJ times EJI. So we can do this because we know how to multiply them, and this becomes EII as long as these two entries are the same, but we're making them the same. And now A commutes with any matrix, so in particular it commutes with this one. So we have EIJ, sorry, EJI, EII. These two can be multiplied, and they give us EIJ and EJI. And then again, I'm going to introduce here, and here. Can you see here down below? Maybe. We have EIJ, EJJ, and EJJ, EJI, which we can do because again, J and J here coincide. And so from this middle part, what we obtain is a multiple, is the J entry of A. So we have that's equal to A JJ EIJ JJ EJ. Okay, and then these three can be collapsed into just one of them, which is the EII. And so what we have is that at the same position, we need to have that the AII, so the ith entry of A, coincide with the jth entry of A. And this is for any I and J between 1 and 10. So that means that every single entry in the diagonal needs to be the same. So A is a multiple of the identity in H. And so we have shown okay, this containment, but the other one is clear. So we have the B of H, or the commutant of B of H, is indeed the complex multiples of the identity. Now, this is only for a finite dimensional. You'll have to do the infinite dimensional case, which is a little bit more complicated, but it can still be done. Okay, so as a consequence, you have the, okay, if you look at the double commutant of B of H, okay, this by definition is the commutant of the commutant. Now, the commutant of B of H, we saw, we just showed that at least in the finite dimensional case, it's just complex multiples of the identity. And then we have the commutant of that, but we see that this is nothing but B of H. So in other words, the double commutant of B of H is itself. You usually have one containment. We saw earlier that B of H is always contained in the double commutant, but the opposite is also true. And if you want one more, we know that B of H is closed under all of the topologies that we saw yesterday. So we have this. That the double commutant, at least for B of H, coincide with the strong operator topology closure of B of H, as well as the weak operator topology closure. And this is actually what the Bicommutant theorem says, which we'll get into just in a minute. We have another example to cover first. Okay, any questions with this? Okay, so I think I'm going a little bit slow, so I'll try to speed this up a little bit, because I do want to do this example, but then the proof, of course. Right, so this is the next example, 1.2.3 in the notes, and this is for measure spaces. So if you take a measure space, or sigma finite measure space, you can see L infinity x mu inside of bounded operators on L2 of x just by multiplication. So you take f and you send it to what we call the multiplication of f. So what this does, it takes a function in L2 and it needs to send it to another L2 function. So at x, it gives you f of x, g of x. And you can check that the resulting function, so this mfg, is still an L2 function. And the reason why is because f is bounded. So we see L infinity inside of bounded operators as a multiplication operator. And it turns out that if you look at L infinity of x mu, and you look at the commutant, well, this is you're seeing as multiplication, so that means that because you're mapping into C, or after logging in, so these are functions from x into C, this will be an abelian algebra, which means it will in particular contain L infinity of x, but moreover, it's actually L infinity of x. Okay, so I'll just tell you the consequence here. Well, if you take L infinity of x mu, and you take the double commutant, well, again, it's the commutant of the commutant, so let's write that out. But now you know that the commutant of L infinity is L infinity. And again, you have one more commutant, but that's just L infinity of x. So again, you have that for this algebra, this the double commutant is equal to itself. Now, again, on the exercise, you have to prove it in this most general case in when you have a sigma finite measure space, but the notes do it in the case when you have L2 of n with counting measure. So n with counting measures. So I'll do that. So I'll try. Should have time, but I might put some speed for this because I want to do the other one more relaxed. Okay. So so if you take any in the natural numbers, you can define in an L infinity function by the following. Sorry, so by En of k is delta n k. So if you treat it n equals speed up 1, otherwise 0. In fact, just you can see by definition this is a bounded function. So it's in it's not only in L2, but it's also L infinity of n. Okay, so let's see in L infinity of n in the content of this infinity of n, seen as bounded in L2 of n. Okay, first, notice that when you take En and you multiply an f, so seen as an operator on P of L to n, and you plug in k, what you have is, well, En k, f of k, and you know that En k is Dirac mass at that point. So you have that this is Fn delta n k, which is nothing but En applied to k. So you can see En acting on a function f in L2 of n by multiplication, just multiplying by the constant Fn. So what we have here is that En applied to f is Fn En. And so if you take t, this element that commutes with every L infinity function, we have the following. So t of f applied to k is, or say n, is the following. Or it will be, it's the same as multiplying by 1. So t f n. But then you can see this as acting by multiplication on this new L2 function. So you have that this is En tf n. And now t commutes with everything that comes from L infinity of n. So t and En commute. So you have t En f n. But then you know what En f is. It's just Fn En. So this ends up being and so what you have here is, if you forget the n's here, you have that t of f is given by f of n t En. So if you call this part g of n, so let me put it in the x force. So if you let g of n be t En n, what you see is that when you add on f, t of f, at n, you're getting g of n times f of n. So what you have here is that this operator t is given by multiplication by this factor, by this gn. So when you apply to f, you're just multiplying it by g of n. And so you can say, well, that means that t has to be an L infinity functions because you're just seeing them as multiplication operators. The only thing that you have left to check is that this gn So this function here is indeed an L infinity function, but okay, so let's do that. So this is less than the norm, the n as an L function, but t is bounded. This is less than t times the norm 2 of the n, which is less than. So this function g is bounded. So this function is in L infinity n. So and it turns out that this map t is given by multiplication by this gn. So we can identify t with this g, which is in L infinity of n. And so that's how you get okay, I guess I'll just put here that L infinity of n prime lies in L infinity n. But again, because the other one, because it's a billion, you have equality. Okay. Right, I know I went a little bit fast, but are there any questions? Okay. Please do interrupt if you do have questions. Okay, so before I present to you the Bicommutant theorem, like we'll see that this thing coming out, so this thing, the double commutant equaling to P of H, or more in particular, being the closure of the strong operator topology. And the weak one, we need a lemma and a definition. So okay, so for the definition, let K in H be a subspace. So for X in P of H, we say K is invariant for X. If when you multiply X by any vector in K, this lands back in K. Moreover, we say K is reducing if K is both invariant for X and X star. So meaning that when you apply X to an element in K, you land back in K, and the same thing for X star. And then as you would suspect, if you have X, so for a subspace, so we say K is reducing, or I guess invariant and therefore reducing for a collection of elements, so for a subspace X. If K is invariant and respectively reducing for every X in X. Okay. All right, so reducing or invariant means just is stable under this under the action of an element X or a subspace, a collection of elements. So this lemma might not seem why it's connected, but it is connected. We'll see in the proof, but it almost says the following. So let M in B of H be a star subalgebra. What this means is that it's closed under star, which will be good. We take K in H to be a closed subspace. And you take P from V of H, the projection onto K, which K exists. The orthogonal projection onto K. Then we have that K is reducing for M. So means everything in M varies K. M is a star. So if so everything includes also the star. So if and only if this projection P is in the commutant. Okay, so it seems like pretty two different statements, but let's see how they connect. So first, let's do the forward implication. So assume that K is reducing. So assume now we want to show that P is in the commutant of M. So we need to show it commutes with everything in M. So let X be mutant. Okay, and then these are operators. So what it means to commute, in some sense, it means that when you take Px and Xp, and you apply it to an element psi in H, they need to give you the exact same thing. Okay, well, K is a closed subspace, so we can divide the elements in H into the ones that land in K and the ones that land in the orthogonal complement of K. So let's do first the ones that land in K. So if we take psi in K, then when we apply P to psi, P is the orthogonal projection of K. So that means that you're leaving this invariant itself, it's already in K. So this is X psi. But K is reducing for N, which means that by definition, X applied to K, when it element in K, will be back in K. And so what we have is, well, this is already in K, this whole thing is in K. So if we apply P to this, we still, it's the exact same thing. So this is, you have equality here. Okay, so now we only need to check what happens in when we are in the orthogonal complement of K. Okay, on one side, we have that P eta is 0 because P is the orthogonal projection on K, so everything outside gives you 0. So when you multiply by X and a 0 vector, you still get 0. So we have that XP on K, the orthogonal complement of K is 0. And what we need to show is that Px is also applied to eta is also 0. Okay, so we show Px eta is also 0. So in other words, we need to show that X eta also lies in the orthogonal complement of K. So if you look X eta, and you take any element inside in K, what we have is, well, we have X eta psi. You can bring the X to the other side. We have eta star psi. But again, K is reducing, meaning that when you apply X star and then an element of K, you still land in K. And this is in the orthogonal complement of K. So this is 0. So what you have is that, and since this was for every psi in K, you have that X eta lives in the orthogonal complement. So when you apply P to this, you'll get 0. So that means that XP and PX are also equal on the orthogonal complement of K, and therefore are equal everywhere. So you have P lies in the commutant of M, as X was arbitrary. So we have the first direction. Any questions? Okay, so for the backwards direction, we assume P is in the commutant of M, and we want to show that P applied, sorry, x for any x in M applied to Neumann in K lies in K. So let x be M psi in K and eta in the orthogonal complement of K. So if you take x psi applied to eta, what we want to show is that this gives us 0. Why? Because if this gives us 0, and this was for any arbitrary element eta in the orthogonal complement of K, that means that, well, x psi lies in the orthogonal, the double orthogonal complement of K, which is just K. Okay, so let's see how we do this. So first we have this. Psi is in K, so that means that when you apply P, you just get psi. So this is the same as putting a P in between here. But then you have P lies in the commutant, so that means it commutes with every element in X, with this X in particular. This is P X psi eta. But then we can bring the P to the other side. It is X psi P eta. P is a projection, so P star is P. But then P is a projection on K. Eta lies in the orthogonal complement, so that means that this is just 0. P eta is 0, therefore it's 0. So as I was saying, what you have is that x psi is in the double perp, which is nothing but the closure of K, but you're assuming K is closed, so it's K. So this shows that it's invariant. For M. But because M is closed under the star and X was arbitrary, you have that you also have it's reducing. Okay. So this is a little, it's a cube lemma. But yeah, there it is somewhere. Is there any question with this? No? No questions? Okay. All right, so then we come to the grand moment of this lecture, which is the Bicommutant theorem, where everything comes together, where these two definitions or these two ideas of one commutator and then the other one of these weak topologies come into place. So this is theorem 1.06. This is called the Bicommutant theorem. And was proven by von Neumann in 1929, so almost 100 years. All right, so the theorem says the following. So it's a very simple, like simply stated, but very nice. Right. So for a unital, stars of algebra, M of VOH, we have the following. Turns out that the strong operator topology closure coincides with the weak operator topology closure, which also coincides with the double commutant. So this is where it all comes together, but it is also kind of mind-blowing. On one side, on the left side, you have a complete description on approximations under weak topologies, but then on the other side, you have something related to commutation, things commuting. And these two turn out to be exactly the same. It's crazy. Here you can see that we'll define a Neumann algebra after the proof as a unital stars of algebra for which that is closed under one of these topologies or for which all of these are satisfied. And so you have in this realm of Neumann algebras, on one side a very analytic component, these approximations, but on the other side a very algebraic component, these being things that commute. So, well, very surprising, but also very cool. Okay, so what we will show for these proofs is the following: that the strong operator topology closure of M is inside the weak operator topology closure, which is inside double commutant, and this is inside, it will be inside the strong operator topology. So we show these three inclusions, and these should give us all. So this one I'm going to call 1, 2, and then 3. So the first one is showing that the strong operator topology closure is inside the weak ones. So this should, I think probably Jon showed you this yesterday. The weak one is much weaker than the strong. It's weaker than the strong. So this implication follows. So we only have to worry about the other two. Okay. All right. So the second one says that the weak operator topology closure is in the double. So we know M itself is always in the double commutant, right? We said this at the beginning. But turns out the things that when you take this limit under this weak operator topology closure is still inside of it. So let's check this. Okay, so let X be in this weak operator topology closure and take Xi be a net in M that converges to X in the weak operator topology. Okay, so what we need to show is that this X is in the double commutant. So that means we need to show that it commutes with an arbitrary element Y in the commutant of M. Okay. So let this and take psi and eta in each. Okay, then what do we have? Okay, then we have xy applied to psi, comma x. That's it. Okay, so what we want to do is the following. We want to show that xy is yx, but this is the same as doing it for every entry in this in the matrix, in every matrix. Okay. So what we'll try to get at the end is that this is yx psi and eta, and because this is for every eta, it would follow that xy psi is equal to yx psi, but then by definition, xy will be equal to yx. So let's see how we do this. First, we can move the x to the other side. So we have y side. Oh, no, sorry. We don't need to do that. So you have x. Then you have that this is just an element. So here you apply y first, psi, and then x. But then y is an operator, so y psi is another vector. And so by the because x psi converges to x in the weak operator topology closure, we have that this is the limit of x psi y applied to psi eta. Now you can remove this. You can just look at xi y. So I don't know if this is big enough. Maybe it is. You have xi and y. Now xi are truly in M, and y is in the commutator of M. So these two commute. So you have limit I of y xi psi eta. Now you would just want to say that, well, send xi to x. You cannot simply do that. Let's first move y to the other side. Start. And now here you have, again, this is just a vector. So you can, by definition of the weak operator topology closure, this is nothing but x psi y star eta, which after you move y to the left side, you have indeed yx psi eta. So we indeed have that xy equals yx. So so x commutes with every element y in n prime, meaning that x is in the double commutant. So we have this. So any limit of x in the at least in the weak operator topology closure still lies in the double commutant M. And now we have the harder containment, which is the last one. That means we want to show that the double commutant is in the strong operator topology closure. Okay. So let x be in this double prime. Now we want to show that x is in the closure of the strong operator topology. So we want to show that it intersects M in these open sets that generate this topology. So I believe you showed you how the open sets look like yesterday. So what we have is that to show x lies in the strong operator closure, we need to show the following. For every n, and for any vector psi1 to psi n in H, and for every epsilon greater than 0, there exists an element y in M such that this y approximates the strong topology arbitrarily well. So x is y applied to psi I is less than epsilon for every I between 1 and n. Okay, so the reason why you have to do this is by definition of how the strong operator topology is. Okay, so let's fix such elements. So fix n, and then psi1 to psi n in H, and epsilon positive. All right, so what we're gonna do is what is called an augmentation argument to make it into a bigger space so that we can use the parallel which I already erased. For y in M, what we're gonna define is phi of y as an operator in V of Hn, direct sum of copies of H, by applying by the diagonal map. So phi of y applied to eta 1 all the way to eta n is simply y eta 1 all the way to y eta n. So if you were thinking this as a matrix, what these 5 of integers would be y. Okay, so in this case, when you see it in this way, you can show, and again, this is another exercise. It turns out that the commutant of n, if you see it in this way, is given by all the matrices, or all these vectors A11, A1n, A1, AN, where each entry is in the commutant of n. And phi of x commutes with all such matrices, with all matrices phi of n prime. By definition, since x is in double commutant. So this is exercise 1.0, where you 1.2.6. Okay, so we have phi of x is in the double commutant of phi of m. Now take S be the closure of of phi of m, phi of y applied to psi 1 all the way to psi n for y in M. This is the closure. This is inside of HM, the direct sum of n h's. Okay, and let P be the orthogonal projection onto this. Okay, well, you can see that S is reducing for pi of M. So by construction, so by definition, S is reducing for pi of M. So then by the prior lemma, so this would be by lemma 1.2.5, so the prior one, it follows that P is projection. Since we have that S is reducing for pi of M, this lies in the commutant of pi of M, and because pi of x was in the double commutant, it implies that pi p times pi x is pi x p. And so what this means is the following. So right. So this means that when you do pi of x sine 1 sine n, what you have is first this vector is in S because 1 is in M, 1 is a unital algebra, so sine 1 to sine n is in M. So that means that you can introduce here a P, because this is the projection onto S. But then these two combine, so this ends up being P of P by x sine 1 all the way to sine n. So therefore this lies in S again, because P projects into S. And so by definition of S being this closure, there exists a y in M such that the difference between pi x sine 1 all the way to sine n minus pi y applied to sine 1 sine n is less than epsilon. But this is nothing but the sum when you apply pi and then you you take this definition, you get sine 1 1 to n pi x sine I x and this y sine I squared all the way to 1/2. And so all of this is less than epsilon, and so each particular one of these is less than epsilon, so you have what you wanted. So x is indeed in the strong operator topology closure. And so you have proven the Bicommutant theorem. So I'm out of time, so I'm just going to say one more thing, which is the definition of a Neumann algebra. Now I'll talk about the two examples that we've seen, and then I'll let you go. Okay, so as you can guess from this theorem, a unital class of algebra M of B of H is a Neumann algebra if M equals to the double commutant, or equivalently, if M is closed under the strong operator topology closure, and it's closed under the weak operator topology. And so this is a Neumann algebra where you have on one side this commutativity, and then on the other side this analytics side. And the two examples that we've seen are B of H. You have to show H for infinite dimensional case. This happens, or at least that B of H is equal to its double commutant. Which I guess we can apply these now, but okay. And then L infinity of X mu when you have a sigma finite measure space. Okay. There's some other properties that you can see, or like other phenomenologies, which I'll let you check directly from your notes because I'm out of time. But thank you so much. If you have any questions, I'll be happy to answer them.
Thank you, Adriana. Does anybody have any questions for her? All right, well, go ahead and soak everything in from the notes. I know this matrix trick always got me the first time I saw it.
Yeah, it is.
So, become one with it. And I guess we will see you all tomorrow.